Let's study the Möbius function. It's an arithmetic function which is defined from the strictly positive integers to complex numbers. It's called mu, and mu of 1 by definition is 1. Mu of n is 0 when n has in its prime factorization a square, and mu of n is minus 1 to the k if n is factorized as p1 up to pk, with p1 up to pk differing primes. So when the number of primes is even, the Möbius function is plus 1, and when it is odd, the Möbius function is minus 1. So now we're going to prove one property of the Möbius function in 3 ways. But before we do that, we're going to prove that the Möbius function is multiplicative. Multiplicative means that if we take mu of m times n, where m and n are co-prime, then this is equal to mu of m times mu of n. Now with this definition of the Möbius function, this is immediate, because if m or n are 1, then this is obviously true. Then suppose that m has some prime factorization, which is p1 up the way to pk, and n has a prime factorization, which is q1 all the way up to ql. Then, of course, since the greatest common divisor of m and n is 1, m times n does not have twice the same prime factor. So all of these factors are different by the assumption of the GCD of m and n is 1. And then they can be an odd number and an odd number, which gives an even number. But that precisely the Möbius function is then going to be minus 1 times minus 1 is plus 1. So this works out. And the same for odd, even, even, odd, and even, even. And therefore, the Möbius function is indeed multiplicative. Now let's come to the property that we want to prove 3 times. And it is that if we sum over all divisors of n mu of d, then it is equal to 0 if n is bigger than 1. It'll be 1 if n is equal to 1. This last part is very easy to prove. So we concentrate on the first part. So let's suppose that n is bigger than 1 and that n has a prime factorization, which is p1 all the way up to pk, where these can now potentially be equal. Then if we sum over divisors of n mu of d, it is equal to, well, the first divisor is 1. Then we can look at all of the divisors with 1 factor. Then we can look at all of the divisors with 2 factors, and so on, all the way up to k factors. And what are then these different terms? Well, they're 1. And here we have a choice of 1 out of k minus 1 plus, and then we have a choice out of 2 out of k plus 1 minus, etc., all the way up to minus 1 to the k, choice of k out of k. But then clearly we can rewrite this as 1 minus 1 to the power k, which is equal to 0. So therefore, we have proven the desired property that the sum of Möbius functions over divisors of n for n bigger than 1 is equal to 0. Now we're going to reprove this in a different way. For that, we're first going to use we're going to use a different property, which we'll prove first. So suppose f is multiplicative. So a multiplicative arithmetic function. Then if we define g as g of n is the sum over the divisors of n of f of d, then g is multiplicative. So let's prove this. This is actually a consequence of the following property. Suppose that n and n prime are co-prime. Then if I have d dividing n and d prime dividing n prime, then the common divisor of d and d prime is of course 1, because they divide n and n prime. And c, which is dd prime, will of course divide n times n prime. And moreover, as d and d prime run over all divisors of n and n prime, dd prime runs over all divisors of n times n prime. So this is the main property we use, because then the rest is easy. G of n prime for n and n prime co-prime is nothing but the sum over the divisors of n and prime. But we can split this into a sum over divisors of n times a sum over divisors of n prime, f of dd prime. And because f is assumed multiplicative, this is nothing but the sum over d divides n f of d times sum d prime divides n prime f of d prime, which is nothing but g of n by definition times g of n prime, which then shows that g is multiplicative indeed. Now we can use this multiplicity of g to give a second proof of the property that we wanted, which was sum d divisors of n mu d is 0 for n bigger than 1. We do this by applying multiplicativity to f is mu, and then g is nothing but sum d that divides n mu of d. So now we have to prove that g is 0, of course, for n bigger than 1. Now g of 1 is 1, g of e to the m by the definition of the Möbius function is nothing but 1 plus mu of p. But mu of p is 0, so this is minus 1, so this is 0. And then by multiplicativity of p of g, it follows that indeed g of n for n bigger than 1 is 0 by prime factorization, and therefore we have proven the property once more. For the third proof, I'll use an alternative definition of the Möbius function, which is that mu of n is equal to the sum over roots, nth roots of unity, but they have to be primitive. So k, first of all, runs from 1 to n, and the GCD, the greatest common divisor of k and n, has to be 1. So this is a primitive nth root of unity. It's not too difficult to understand that if we sum over the divisors of n mu d, this is nothing but the full sum over nth roots of unity, because since every nth root of unity is a primitive dth root of unity for a unique divisor d of n. And then the full sum over nth roots of unity is well known to be 0 for n bigger than 1. For instance, by thinking about the equation z to the n is equal to 1, and then decomposing it as z minus z1, etc., z minus zn And then one sees that the term, it's z to the power n minus 1, is 0, and therefore the full sum over the nth roots of unity is 0. To understand how this works, for instance, for n equal 4, what are the fourth roots of unity? 1 e to the 2 pi I over 4, e to the 2 pi I times over 2, and e to the 2 pi I 3 over 4. So these are primitive roots, fourth roots of unity. But then we have the divisor 2, for which we have one primitive root of order 2, and then we have one primitive root of order 1. So this indeed corresponds to the sum over divisors of 4, where the primitive roots correspond to 1, this corresponds to 2, and this corresponds to d equal 4. So these are 3 proofs of the property of the Möbius function that the sum over the divisors of n, mu of d, is equal to 0 for n bigger than 1. This property will be useful in Möbius inversion, as well as Dirichlet convolution. And those are useful in arithmetic computations.